orbited around the Sun many times, it loses its icy gaseous components, becoming essentially dormant and showing a dry surface that resembles a carbonaceous chondrite asteroid, which contains many water-bearing minerals.
We're looking at meteorites now, which we always assumed always just came from asteroids, and wondering, which of these could have come from comets. What that tells us is that there are many different kinds of comets. They've all had different histories, just like asteroids have.
Asteroids and comets have much more in common than just physical and chemical composition. They've both left deep scars on Earth, resulting in the extermination of life, time and time again. Near-Earth objects are asteroids and comets whose orbits bring them close to Earth's orbit. In the case of asteroids, Jupiter's gravity, or light pressure from the Sun, can nudge these cosmic relics out of the asteroid belt. Similarly, the gravity from Neptune can push comets out of the Kuiper belt. The scars from asteroid impacts can be seen throughout our solar system. All the terrestrial planets and moons show the marks of these deadly blows, including the Yucatan Peninsula, near the modern village of Chicxulub in Mexico, producing a kinetic energy equivalent to 800 Hiroshima atomic bombs. The impact left a crater in the ocean more than 110 miles across and 20 times as deep as the Grand Canyon.
Because the impact event hit a sea, simultaneously, this created tsunami-sized ripples that then crashed onto the shoreline of the Gulf of Mexico. The energy and the explosive ejection of that material from the crater was so dramatic that that molten debris actually blanketed all of North America. Life as we know it would have been virtually erased.
Many scientists now believe the impact was responsible for wiping out 75% of animal and plant species on land and sea, including the dinosaurs. Planetary geologist David Kring is a leading expert on asteroid impact events.
We now understand that impact events aren't simply a geologic process that excavates a bowl-shaped cavity, but one that actually can affect the environment, whether it be local, regional, or global.
In 2001, Kring headed up the Chicxulub scientific drilling project near the impact site in the Yucatan Peninsula. His goal was to find evidence that the Chicxulub impact produced worldwide climate effects by drilling down to the rock dating to that time period.
The drilling project confirmed our suspicions that the impact event had collided with a series of very important rock types, limestone and anhydrite. The limestone, when vaporized, produced greenhouse-warming carbon dioxide, and the anhydrite, when vaporized, produced sulfuric acid rain. And so this confirmed some of the global climatic effects produced by the Chicxulub impact event.
The Chicxulub scientific drilling project also revealed that the impact generated hydrothermal systems which spanned the entire diameter of the crater, providing critical environments for new life to evolve. The next Chicxulub-sized impact is estimated to occur 35 million years from now. But one can never be too when it comes to space rocks.
Unfortunately, these types of things do not occur like clockwork. In fact, the next Chicxulub-size impact event could occur tomorrow.
Many scientists are confident that a cosmic impact was responsible for wiping out the dinosaur. But they're still debating what type of rock was responsible.
We aren't actually sure whether this was an impacting asteroid or an impacting comet, although the bulk of the evidence points towards an asteroid. Asteroids, in fact, dominate the flux of impacting debris to the Earth. Somewhere on the order of 85 to 95% of the objects that asteroid belt.
If we do find a comet on an Earth-threatening trajectory, it might be difficult to deflect or destroy before it inflicts apocalyptic destruction. Although most potentially hazardous objects are asteroids, comets remain a legitimate threat. These icy bodies, which come from the outer solar system, can travel 3 times faster than asteroids, so it only takes 9 months for them to get from the orbit of Jupiter to the orbit of Earth.
You couldn't plan years ahead for an impact from most comets. You'd hear about it maybe a few weeks ahead, maybe months at the most.
Fortunately, Jupiter acts as a planetary shield, deflecting or absorbing comets that drift towards Earth. And scientists now have the pictures to prove it. On the 22nd of July, 1994, telescopes around the world caught a glimpse of one of the most violent comet impacts in the history of the world. A string of about 20 comet fragments, named Shoemaker-Levy 9, crashed into the upper cloud decks of Jupiter at speeds 100 times faster than a speeding bullet. Since gaseous Jupiter doesn't have a solid surface, the objects were slowed down by its thick atmosphere and exploded as airbursts, creating plumes visible from Earth. At Sandia National Laboratories in Albuquerque, New Mexico, physicist Mark Boslow and his colleagues predetermined that this cosmic spectacle would be seen from Earth through computer simulations.
People really did not expect this to be observable, partly because the location of the impacts were actually over the horizon, over the limb of Jupiter as viewed from the Earth. We simulated the interaction of the fragments with Jupiter's atmosphere at high velocity, and the giant plume that was ejected out into space and could be seen rising over Jupiter's horizon as viewed from the Earth and from the Hubble Space Telescope.
Armed with new knowledge about airburst impacts, Boslow began reinvestigating a similar event that happened not too long ago. On the 30th of June, 1908, the biggest cosmic disaster in recorded human history occurred in Russia. A large object exploded in Siberia's remote Tunguska wilderness. The blast ignited heat and shock waves, which toppled 80 million trees over an 800 square mile area. Yet no one was directly killed because the area was relatively uninhabited. The Tunguska disaster has baffled scientists for a century because no impact crater or meteorite has ever been found, and many of the trees in the area were flattened but not incinerated. Many scientists finally came to the conclusion that a space rock exploded as an airburst when it hit our atmosphere.
So this was an atmospheric explosion. It was really the only one we knew about, which made it seem unusual, very much like the Jupiter impact, and that in fact these are probably more common than we had really thought.
The asteroid was originally calculated to be 200 feet in diameter, releasing 10 to 15 megatons of energy, based on the devastation in the area. But Boslow now thinks the size was much smaller.
When I did the simulation with a 15 megaton impactor, the fireball, the very hot gas that emerged from the explosion, descended all the way to the surface. That would have incinerated all the trees and created this zone of complete devastation that was not observed at Tunguska. The trees were not incinerated. Therefore, the mass would have had to have been less than people had previously thought.
Boslow designed new simulations to show that the momentum effect of the air blast, not the size of the rock, caused the devastation.
I modeled this as an object coming in at a 35-degree angle, and I exploded it when it descended below about 7 or 8 miles above the surface. comes in, explodes, but the jet of hot material continues to descend. So what you see is the momentum effect after the explosion. The momentum is the velocity that continues to carry the mass downward before it finally slows down and stops.
Boslow's new simulations also allow for the fact that the terrain wasn't flat, so the winds from the blast were amplified by the ridgelines.
But the gust is stronger on the top of the ridge, and just beyond the top of the ridge, that's where you would tend to have the most trees and the most damage.
Boslow's new research may mean that finding smaller asteroids is more important than previously thought.
One of the conclusions that results from this work is that smaller asteroids can create significant damage at the surface.
It's not a matter of if, but when we'll be hit by another Tunguska object. It's estimated to happen once every 500 years. And with Earth being more populated today, such an impact could be deadly. Asteroid and comet impacts are not events of the past. Our planet is hit by football-sized space rocks every day. Most go unseen. But in 1992, amateur video caught a meteorite flash across the nighttime sky. It eventually crushed the back of a parked car on the outskirts of New York. The odds of being struck by small or even large meteorites are extremely low, but the potential harm one could cause keeps NASA on high alert. Congress mandated that NASA must detect over 90% of near-Earth objects over half a mile in diameter. These rocks could strike the Earth with an energy greater than all the nuclear weapons on our planet today. The most potentially hazardous near-Earth asteroid to date is Apophis, the size of a large city block. This space rock will pass close to the Earth on the 13th of April, 2029.
Apophis has a 1 in about 45,000 chance of impacting the Earth. That is cause for at least some concern. Even though the probabilities are very low, it's not all that big as asteroids go, but if it were to fall on a city, it would obliterate the city.
It's still a minuscule probability, but it's not zero. I think a really good idea is to put a transponder on it that can be used to track it very accurately. Then we can know if it's a threat or not.
Scientists are developing mitigating technologies to either destroy a near-Earth asteroid like Apophis or nudge it out of harm's way. But as much as asteroids and comets are life-threatening, they could also one day be life